Here you are. You may introduce yourself, and let's start.
Okay, thank you. Hello, dear students, colleagues, all the participants of this lecture. Now I will share the screen with my presentation and introduce myself. So I hope everything is clear and the presentation is full screen. Yeah, it's okay.
Yes, full screen.
Okay. Good evening once more. My name is Andrei Kuznetsov. I work in Sber AI and the position of team lead in computer vision projects. One of the main research topics of my team concerns diffusion models and text to image generation models. And today I'm going to make a deep dive in this topic, just for you to be more familiar with it. You should get more information about this topic, and later I will share the presentation for you to maybe get more details on some specific aspects of the presentation. The content of today's presentation will be as follows. So first, I will speak a little bit about the task history, how generative content appeared, how it was developed through several years. Then I will speak about the diffusion process itself. The diffusion process itself. Then we'll speak about a little bit about existing diffusion architectures or different types of architectures. Then I will describe our latest model, Kandinsky 2.1, tell you some information about experiments a little bit and achievements after the official release on the past week, the previous week, on the 4th of April, when we released Kandinsky, and some common words in conclusion, and maybe answer questions and so on. So I think we can start. So speaking about the task history, most problems in computer vision, like classification and segmentation, are well known, and they are usually solved in one modality. This means that we take one type of images, usually, something like medical images or remote sensing data or ordinary images, and solve different downstream tasks like classification, segmentation, and so on. And this was the most important and the most commonly used topics for different conferences, for different lectures and scientific research. But in 2014, generative adversarial networks appeared, and this gave a very, very big boost in development of generative models. People started to train these types of networks to solve different tasks of generating content. And by 2016, the main research is was focused on the unimodal architectures, and this approach changed. So after 2016, the first mention of generative models that could create images by text descriptions appeared on such big conferences like ICML and NIPS. So this year is usually called as the start of generative models development. And from 2017, actually, no machine learning conference of A or A star rating were without these publications on the topic of image synthesis from some textual prompts. So here are some examples of these papers. And actually, if we take a brief look on the history from 2016, we can see that in Scopus and in Web of Science, libraries, we could see a rapid increase of the number of papers on these topics. And in 2021, the first most hype and well-known networks appeared. These were DALL-E by OpenAI, Clip by OpenAI, and Cogview by a Chinese university. So all these years, we can see that the number of papers increases, and in 2022 and further, this trend didn't change. So, what is a diffusion process? Actually, there are known 4 different types of architectures that are used to generate some content. And diffusion models, they are different from other approaches because it is some iterative process that is usually used to add Gaussian noise iteratively for some input data. So this approach is very well presented on a sample of images like this. So actually, in the papers, this process is usually called like denosing diffusion probabilistic models. And on further slides, I will make a brief look at the process, and if needed, we can come back to these details later, or make a special lecture on this, because it is a very broad topic, and it is quite difficult to describe it fast. So the diffusion process consists of 2 main sub-processes. The first one is the forward diffusion process, which means that we have on the left the initial clear data, and during the forward diffusion process, on every next step, we add some Gaussian noise to the data. And this iterative process, by the end, leads us to some uncorrelated noise. The reverse denoising process means something that we use in generating images by textual prompts. So we have the initial noise, and we try to recover, to denoise this initial data, to denoise it in a reverse way to get the initial data as precise as we can. So this process that is called reverse denosing process is the core idea of diffusion models that are used in practice nowadays. So if we go into details of the forward diffusion, here we can see a conditional probability Q that just shows the correlation between the next step of diffusion process and the previous one. So xt conditioned xt minus 1 is just a normal distribution with the following mean and deviation. And actually, using the rule of multiplicating the probabilities, we can see that the initial state of our data depends on all the previous states. So all the further steps depend conditioned by the x0. And here we can see the 2 steps of this diffusion process. And here is the Q, which shows that this next step depends on the previous step by adding some part of Gaussian noise. And the idea is to find out the reverse dependency, the reverse condition probability, just to find out how we can recover the initial data if we know the forward process function. To implement and to find out the dependency not from the by the next step from the previous one, we can calculate the diffusion kernel just calculate it mathematically and find out that we can actually calculate the probability of every step in this forward diffusion process from conditioned by the zero step. This is because every second step has a fixed mean and standard deviation from a specific period of mean and standard deviation of the noise. This is why we can calculate this mathematically, how x step with the index n depends from x with index 0. And here how the diffused data distribution looks like. It consists of the input data distribution and diffusion kernel. And if we know the input data, we can actually calculate the latest step of this process. And this is usually called sampling. So every other state leads us to some normal distribution. So this is the initial data. This is the sample from the distribution queue. And here, every other step, adding some part of some Gaussian noise, we calculate it, add it on the every other step, and in the end, we can find out that the image becomes actually Gaussian noise. So here, how it looks like the right image in the row. Data generation from the denoising through the denoising process consists of two main steps. It's data sampling and iterative data sampling. So we estimate the number of sampling, the number of samples that we need to do, the number of steps during the sampling process, and this usually leads to better recovery of our data because the more steps we do, the more precise image we usually recover or denoise from the initial noise. And in general case, this distribution queue can be approximated just by normal distribution if the parameter of standard deviation is extremely small. So the standard deviation usually selected very small, just to be close to zero, to make this distribution very slow growing. So when we find out and understand how the forward diffusion process works, we can estimate how the reverse denoising process works. And this is usually, as I already called it, generative diffusion process. Here we need to estimate the inverse probability. Because we know the forward process, we can estimate using this calculation. We can estimate the probability from the xt, the noised image. We can estimate every other step of our sampling process in a reverse way, just to find out how it will look like if we want to estimate the probability of sample x with index 0. And here is the trainable network. So every step of our backward process or reverse process is estimated as an inverse mu function, which depends on some parameters theta. And we do the following process. So it looks like the same calculation of multiplication of probabilities, the same rule. So these are some details on the training with the variational upper bound calculation. Actually, we can just find out that there are several main functions in the loss function. I will not go into details because I leave a link to the paper, and just looking to the paper, you can find out how these calculations are received. So actually, it is already a Kullback-Leibler divergence, which is estimated for different steps of our diffusion process. And this leads to estimating the next step of diffusion process. And this is how this reverse diffusion process is usually working. So this is the same written in pseudocode, just to understand how the sampling, how the training works when we calculate the gradient descent step on every step of our training of diffusion model, and the inference step of sampling when we have the trained model and we want to use some T large steps to generate our image. So, and here we can see that how we calculate every other step. So we start with T, which is the noise image, and then going T lower -1, we estimate every other step, and this is how we come at the end by T equal 1 and X with index 0, we calculate the final recovered image by our model. And the model is actually here. So speaking about the existing diffusion models, I will show there are three main models that are well known from the previous year. The first one was developed by the company OpenAI. The key features of this architecture is that the text description or the text prompt that is coming to the model is fed to the text encoder input. Then we have some prior model that is used to estimate some prior image between the text encoding and the corresponding visual encoding. And here we can see the well-known CLIP model, which is already developed by OpenAI in 2021, which is usually understood as a model that can find out the similarity of text and image in one vector space. And another one part of this model is the decoder model, which is actually a UNet-like architecture, which is a diffusion model, which stochastically generates an image iteratively step by step. So it's a diffusion process. So here it is, and here is the prior. The model was not open source, and actually we cannot find out how it works in real life. I should mention that it works in pixel space. Everything works in pixel space. Imagen was developed by Google. The idea is practically the same, with the following difference that every other step of the diffusion modeling or diffusion process was made iteratively to increase the resolution of the generated images. So we have some large language model as a frozen text encoder. Then we use this text embedding to create a 64 by 64 pixels image. This is the core text-to-image diffusion model. And then using the same text embedding and this image conditioned with this text embedding, we have two different super resolution models. The first one extends the resolution to 256 pixels. And then the super resolution diffusion model, the latest one, the last one, generates image in the resolution of 2024 pixels. And this works actually good, according to the paper. The only problem is that if we have some artifacts in the image 64 by 64 pixels, then these artifacts will extend on every other super resolution step. And at the same time, it is quite a complex operation in terms of computational complexity. And the third one approach, it works in latent space. What does it mean? It means that we do not try to recover by the diffusion process the initial image. So we do not work in the pixel space. We work in the latent space. This means that we use some encoder and decoder or autoencoder network, for example, some VQ via network, that can represent the initial image into some latent space and latent vector space. And we tried to use diffusion process just to recover this latent representation of the vector. And then we have the image encoder part, image decoder part, which is used just to recover the initial image. This is much faster. This is easier to implement, easier to train, because the resolution, or we do not depend on the resolution of the image. We just have some dimension of our vector space and use it as a representation of our images. And this is much better to work. So when we developed Kandinsky, we first started with the idea of latent diffusion and used it as the core of our architecture 2.0. The main idea that we tried to implement was to make the model multilingual. So we used two different text encoders, XLMR by clip and the model MT5 small. So every input text was encoded by two different models. Then we concatenated all these embeddings into one, and through layer norming, put it in the UNet to recover the latent space of our image. And then use the decoder, which we used VQGN, just to decode the image. The UNet architecture consisted of 1.2 billion parameters, and these two multilingual text encoders were used to extract the latent space to understand different languages. All the generations are presented here. The model was very good in interpretation of prompts in different languages and in different styles. So, but it was not good in some specific detailed generation of faces, of some interesting prompts. So the quality was still not very good enough. So we started to develop this architecture and decided to add the image prime model to our latent space. Just to take all the information we received from training of Kandinsky 2.0. So this UNet architecture that is in the violet rectangle. So we wanted to inherit all the information and all the data that we used for training this big diffusion model. So we changed the architecture and released it last week. Now it contains 3.3 billion parameters and looks like this. The core of Kandinsky 2.0 is a latent diffusion, which inherits all the unit weights of Kandinsky 2.0. And this latent diffusion unit is the green one block, which you can see here. The left one row shows the diffusion mapping process, the diffusion mapping training. This is how the image prime model appears. So we have the model clip, which gives us image encoder for an image, and the same model gives us a text encoder for the text input. This is the model, as I already said, that could put in one vector space text data and image data. And we trained the diffusion mapping for these two types of encoded data, and used it further on the text to image generation process. It's in the middle one, in the following way. When we train the diffusion mapping, we take the text input which the user prints in somewhere in Telegram bot or website, something that he uses as input. We use clear text encoder to encode this data. Then we use diffusion mapping to get the mapped image encoder representation using this diffusion model, which conditioned on the text clip. And then we use this clip encoded information for the text input. The image representation in the latent space of clip embeddings from this red model, which is the image prior model. We combine it in the latent diffusion UNet model that we took from Kandinsky 2.0 and receive the new latent representation of the image during the main diffusion process, reverse diffusion process. Generate this latent representation and use a new decoder MoVQ to decode the latent representation of the image and receive the initial image itself. The image itself now is generated in the resolution of 768 pixels, and it works only for aspect ratio of equal sizes, so only square images are generated. But in the nearest update, we will change it because there were some experiments on different aspect ratio images. So the main idea which leads to the better generation of images is the new image encoder decoder MoVQ, and this image prior model, which we call diffusion mapping, to map text encoders, text embeddings to image embeddings in the clip embedding space. So overall, our new model has several important features, and it can generate images by text. It can mix two images. It can make a mix of image and text. It can take an image as input and create new image variations because it can find some similar latent representations in the latent space and decode it to receive the nearest one. And of course, in painting and outpainting, features are also available. So this is some information about the size of different parts of the model, and actually just for information. So further, I will show some interesting results and beautiful pictures of different prompts, which are generated by different features of our network. So here is a simple text-to-image generation. You can see how the new model understands the text prompt in details, and it works in different languages, in Russian, in English, and the other ones. Mixing images works very good when we want to mix some image and a style image, for example. So here you can see that adding as a style the view from the red square, we can find that this girl from the original image appears similarly on the red square on the background. Text mixing and with images helps us to manipulate the image using this text prompt. Now we work in the direction of instructive tuning, just to ask the model to change some part of an image according to the prompt, not the whole image, but only some specific part. Image variations, as I said, we can take some initial input image and receive several images that are similar to it. In painting, we take an image, we use the brush to delete some part of the image and give a prompt to fill this part of the image. So here I printed a red shining sport car standing on the road in full palette and full color palette, 4K style, with high details. And here we can see that this part of the image that I removed was quite good. Implemented the embedding of this part of an image with some view of a car. So outpainting, it's actually the same, but this helps us to extend the size of the image to make it different aspect ratios at the moment. Speaking about experiments, FID, it's Frechet assumptions distance. It's one of the main metrics that I used to calculate the quality of generative models. Actually, it is based on the Kullback-Leibler divergence equation and helps us to find out the similarity between two distributions, two functions of distributions. We take the COCO 30K validation dataset, take prompts from this dataset, generate by these prompts images by our model, and compare these distributions, the original ones and the generated ones by the same prompts. And here we can see the position of our model in terms of different architectures well known in the world. So the less the value of FID, the better the model works. And actually now we are on the third place after Diffie by NVIDIA and Imagen by Google. The other models show much lower results. And here is also the Kandinsky 2.0, the Kandinsky 1.0, which is an autoregressive architecture. So these are different results. To test the model, now you can use different ways. You can use Kandinsky bot in Telegram. You can use fusionbrain.ai website, where you can use in-painting and out-painting features. In Telegram, you have generating by text, fusing images and text, and actually generate similar images. The website rudali.ru and the feature of salute devices, where you can ask the assistant to turn on the painter and to ask it to generate some image. It uses Kandinsky 2.0 model. So further, I will show some ways, some examples of working of our model in different websites. By the 12th of April, after the official release of our model, we now have actually 15 million queries, which are distributed in the following way, as it is shown on the website, or it is shown on the slide, between Telegram bot, fusionbrain.ai, rudali.ru, and salute devices. And the overall number of unique users is more than 2 million users. And actually we beat OpenAI ChatGPT record, where they showed 1 million unique users after 5 days when officially released ChatGPT. We did the same, the same number of unique users by 4 days. The detailed statistics show how many queries in hour we have every day. The main peak was on the 8th of April. Here we had practically 150 queries an hour because there was a very big promo company and a lot of popular bloggers and websites showed and told about the quality of our generations, and a lot of people from these websites and resources came to our backend server with different queries of to generate something from their text prompts. Most of the users are from Russia, but already there are people from Belarus, Kazakhstan, Germany, USA, and others. And here we can see how the distribution of queries extends, and then now it is a little bit going slower. We also analyzed the query topics. Most of them are concentrated in the following clusters, and each cluster is called by the is unified by some topics. For example, this blue one is the description of people and animals. The big orange in the middle is a description of some places and different objects or landmarks. The brown one is a description of some actions of people and animals. Some well-known persons are in this part of this map. The green one, for example, is different styles. When people try to generate, for example, Spider-Man in the style of Miyazaki, and so on. So actually, it's a very interesting map, which showed how the queries were distributed. Here are the links to our spaces in Hugging Face and to the repo in GitHub. Also, we made a comparison with Devron that was released by Yandex a day later on the 5th of April. We tried different prompts to give it to our network and to Devron. And here we see that Kandinsky showed much more detailed results than Devron. In the Russian community, the feedback was very good. Different people that tried the model, they wrote mostly good comments. They tried the model in different different features of our model in bot, on the website. There were some problems on the first days with the queries processing, but we changed the backend server on the third day on the fourth day after release, and it became more stable. The international community also reacted very good. For example, we saw an overview on medium.com. The CTO of Hugging Face colleague wrote about our model in his Twitter. And on Reddit, there was a very big sequence of comments to the post about Kandinsky 2.0. Also, there was an overview and comparison of Kandinsky 2.1 with Midjourney on YouTube, and this is mostly was written because Midjourney closed its open use in Discord, and now it is paid. Free use of Discord bot is closed. Now our model was much better in terms of easy of usage. Speaking about the publication on Hubber, it's the second place in best papers on the 4th of April. The GitHub statistics is already shown here. A lot of pull requests are already done, a lot of forks. In the beginning of the process, the Kandinsky 2 repo had actually 200 or 300, 200 stars, and now it is more than 1,200. We also got the 4th place in GitHub Trends on the day of release, and the next one. So I think it's also a very good result. The link to Hugging Face, 2 interesting platforms and web studios to deploying different models like replicate.co and fups.ai. They implemented our model on their websites just to extend the usage of our model in different spaces. And already fups.ai has its marketplace of images where a lot of images appear every day. I just connected yesterday to this website in the evening and checked that different new images appear on the website generated by our model, and they are published here to reach money. So this is about 1 million unique users in 4 days. It was a very popular news. This is information about how we can use Kandinsky in product applications, for example, for marketing visuals, for generating logos and icons for different companies, for interior design and architecture design, dress concepts, image stylization. So a lot of applications of using generative content can be imagined, and this is why I put 2 times 3 dots, because actually anyone who works with images can imagine new applications for such models in industry or for some research, for example. So in conclusion, I would like to say that the model itself and the approach itself is very popular now. It develops, a lot of new approaches appear, a lot of different updates are made every day. Actually, the community made a lot of work for the development of these approaches, for these models. Different web UI interfaces appear, different collaborations appear. A lot of people want to create some extraordinary arts just to sell it, just to make some specific interesting wallpapers, or just pictures to resend each other, for example, for invitating someone or to congratulate someone. So the applications of this approach and of this scientific research is much more wider and broader than we can imagine or could imagine last year. Now the trend is going to text to video generation, and I think that this year will be devoted to these models development, and we want to go in this direction also. I would like to invite everyone who didn't try Kandinsky to do this, to make your own experience, to get your own experience with working with this model, and maybe write your feedback if it's good or bad, and if there are some bad prompts or bad results. We know that it works not very good with fingers yet, with quantitative elements, with some specific Russian domain, specific Russian domain figures, for example, or characters like Cheburashka and Carlson and many others. And we work in this direction to improve the model, to improve the quality of it, and hope that in summer you will see the updated version of our model. However, you can write the questions to me directly if you have. I will answer them, or we will discuss with our team if there are some good ideas to implement in the further versions. So my team is ready to work to develop the model, and we'll be glad for any feedback. And some advertisement of my channel, where I write all the interesting things about different AI news, new models in multimodal research or in generative research. Thank you very much for your attention. We'll be glad to answer your questions or to write them personally to you. Thank you.
Да, Андрей, спасибо. Большое количество вопросов в чате, поэтому, пожалуйста, и отвечать на русском можно, так как вопросы на русском. Видно чат?
Угу. Да, чат
Все.
видно. Так, если вам тут интереснее, полезнее. Так, значит, мастер-классы плюс-плюс-плюс. Welcome на русском. И запись на YouTube, наверное,
Слушай, лучше
будет.
сначала. Перейди в самое начало, или хочешь, я тебе прочитаю?
Ну,
Вот там,
давай
как
в
вы
самое
пришли к
начало.
архитектуре?
Да, самый первый, это как вы пришли к архитектуре Кандинской, убралась ли какая-то известная архитектура или полностью с нуля?
Слушай, у меня почему-то... вот, все увидел. Алексей Березкин. Так, как
Да,
пришли к архитектуре
1926.
Кандинского? Начинали мы с того, что пробовали имплементировать именно латентную диффузию и поиграться с ней. Потом появились идеи относительно того, чтобы закрутить туда мультиязычность и попытаться из этого создать какое-то интересное представление мультиязычное. Там были интересные результаты в том смысле, что можно один и тот же запрос писать на разных языках, и он тебе будет генерировать специализированную информацию. Например, можно написать там запрос в стиле «самое популярное блюдо». Вот на русском ты его напишешь, там будет какой-то что-то связанное, допустим, с борщом, там, с щами, с чем-то таким. Если ты напишешь это на японском языке, то там появлялись картинки роллов и так далее. Ну, то есть это интересно. Вот. Все, что касается дальнейших изменений, это уже все были как бы внутренние эксперименты и доработки, и мультиплеер добавленный, и докрученная там модель нового декодера картиночного, который просто очень сильно забустил по качеству в картинках. Ну, в общем, это все просто результат большого количества экспериментов на нашем кластере. Так, наша группа в Telegram, там все оповещения. Я уже пробую, это классно,
моё.
лучше, чем Midjourney. Спасибо, хорошо, что лучше, чем Midjourney. Ну, на самом деле, до Midjourney V5 нам еще стоит подтянуться, и мы вот сейчас как раз идем в этом направлении в части увеличения модели. А что касается Midjourney, ну, наверное, на уровне V4 где-то вот мы сейчас находимся в текущей версии Kandinsky. Так, спасибо за лекцию. Пока не используем, но собираем эту информацию, потому что действительно это очень полезно. И вот на прошлой версии Кандинского у нас даже на сайте Рудали есть возможность типа пролайкать, понравилась тебе сгенерированная картинка или нет. В остальных ситуациях пока этого нету, в остальных источниках, но на самом деле кажется, что это полезная информация, особенно если это так скоррелировать с чат-GPT, где можно через RL с человеческим фидбэком попытаться что-то улучшать, может быть, это и даст буст. Но я не уверен, что это будет хорошо работать в картиночной, в визуальной области, потому что, скажем так, если текст еще можно верифицировать, правильный ли он или нет, фактологически, то вот картинка, когда ты просишь нарисовать, это все настолько субъективно, кому-то кажется она похожей на запрос, кому-то не похожей. Вот, в общем, не очень уверен, что это может сработать в пользу. Может даже наоборот какие-то байсы создать в пространстве визуальном. В общем, идея хорошая, но надо с ней, аккуратно. Так. Организовать встречу с деталями программы. Так, если можно задать вопрос по latent diffusion, я немножко все начали. Можете подробить, как это хорошо, так, латентная диффузия – это когда мы восстанавливаем диффузионным процессом не саму картинку попиксельно, а восстанавливаем ее промежуточное представление, то есть просто вектор в пространстве признаков. И это проще и быстрее работает, потому что вектор явно более короткий по длине, чем картинка целиком. И это ускоряет как процесс обучения, так и процесс восстановления и инференса. И вот работать с латентным представлением всегда проще, потому что с ним его очень легко переучивать. То есть если вдруг вы меняете тип, допустим, энкодера, вот как у нас был в Кандинском 2.0 визуальный энкодер Сбер Вакуган, и мы буквально там за день переучили на совершенно новый энкодер картиночный, вот этот MovaQ, что позволило нам получить большой прирост в качестве. И это там, для этого мы использовали штуки 4 или 8 карточек А100. То есть совсем немного по сравнению там с обучением. И вообще интегрально получилось так, что Кандинский и все его версии по вычислительным ресурсам и затратам, за что нас сильно там ругали в общественном поле, когда мы учили первого Кандинского авторегрессионного, что мы много ресурсов прожгли и сделали самый большой вычислительный проект в России. В этот раз, ну, он по сравнению с Кандинским не сильно большой. Вот латентное представление, латентная диффузия как раз в этом смысле позволяет получать определенное ускорение. Так.
Прежде чем перейдем к следующему вопросу, там вдогонку к этому Алексей написал самый-самый последний вопрос прокрутить, если прочитать.
Так, латентная диффузия получается как аналог эмбеддинга для высокой... Ну да, по сути эмбеддинги, да, все так. Просто работать с пространством эмбеддингов. То есть генерируем эмбеддинги, потом декодим из них, получаем картинку. Так, насколько параметризованный запрос? Запрос ожидаемый результат. Мы сравнивали по некоторым типам запросов с Midjourney, пока он был бесплатный. С DALL-E 2 не с чем сравниться, кроме статьи, потому что ну, у них, по-моему, они выпускали тут свою модель по платному доступу, но, честно говоря, с ними не сравнивали. Сравнивали только по фидам по статье. С Midjourney сравнивали, со Stable Diffusion сравнивали. Ну, что-то лучше, что-то хуже получается. То есть не могу сказать однозначно, что прям есть однозначная победа во всех направлениях, но вот в некоторых доменах лучше, в некоторых доменах хуже понимаю. Параметризован. По поводу параметризации, ну, по сути, если вот залезть в код инференса диффузии 2.1, то там из параметров что? Значит, параметр скалирования этого диффузионный, количество шагов диффузии, и это и для приора, ну, то есть gradient scale, для диффузии приора и для диффузии основной. Это по параметрам. И еще добавили негативные промпты в оба типа диффузии, да, в обе модели. И, в принципе, через негативные промпты вот нам удается, например, там, генерировать картинки с правильным пальцем. Я там на слайде девочку показывал в самом начале. Вот, то есть, в принципе, негативные промпты помогают справляться с рядом сложностей. Попробуйте Control.net. Да, хорошая штука. Очень хочется, чтобы вот нам как-то в таком же направлении добиться, сделать что-то типа Automatic 4 единички, вот то, что сделали в WebUI вокруг Stable Diffusion. Ну, то есть комьюнити, надежда большая на то, что тоже будет подключаться к развитию нашей модельки. Более низкое, но может быть, как происходит изменение картинки по промпту текста, как модель упирает в какие части, как она будет изменять. А то, понимаю, слишком поверхностно. Смотрите, есть такой механизм внимания, attention, да, и он позволяет строить корреляцию между текстом и картинкой. И когда модель учится, она на вот большом количестве пар текст и картинка пытается уловить эту закономерность, то есть понять, какое слово больше влияет на те образы в картинке, которые находятся. То есть пытается строить вот эту зависимость через механизм внимания. И механизм внимания, cross-attention, он как раз и позволяет нам уловить, поймать зависимость между текстовой частью и картиночной. И вот от этого как раз модель и выбирает, как она будет генерировать картинку. Ввиду того, что у нас появился механизм image prior, нам помимо текстовой части еще получается, что мы можем картиночную затравку давать из модели Clip, которая позволяет нам тоже учитывать ее как некоторую предварительную априорную информацию при генерации конечной картинки. Используется при Infinity. При Infinity он тоже используется, потому что мы же, когда генерируем картинку, мы же обращаем внимание на определенные слова. То есть оно проходит через UNet и приходит в итоге к результирующему латентному представлению картинки, которая уже восстанавливается. Вот если там по... Сейчас мотаю. Вот. То есть у нас модель проходит через текстовый энкодер, потом через Diffusion Mapping у нас получается промежуточный латентный вектор в пространстве клип-эмбеддингов картинки, и вот он вместе с кодированным представлением текста попадает уже в латентную диффузию в UNet, из которой у нас как раз получается декодер. Ну вот в зависимости от того, какие туда попадают связанные вещи, связанные там понятия текста и картинки, у нас диффузия восстанавливает нужную нужное представление эмбеддинга картиночного. После этого мы уже можем его декодить. В принципе, вот здесь как раз и завязана вся зависимость между картинкой и текстом. Вроде бы все.
Ну, там еще было что-то про стажировку.
Ну,
Вот, возможно, время после магистерской программы. Да, кстати, у меня сейчас есть еще одна стажерская ставка, поэтому присылайте резюме.
Ну, они
пишите.
периодически появляются, да, это понятно. То есть такая.
Да.
Ну, в общем-то, спасибо огромное за такую интересную встречу. Такое количество вопросов я давно не помню. Я благодарю вас, Андрей. Я благодарю наших студентов,
Спасибо.
второкурсников, кто все-таки тоже подключился к нам. Молодцы, ребят. Я думаю, что вам будет это полезно. Те, кто еще не наши студенты, я хотела бы отметить, что примерно в таком формате проходят лекции по нашим курсам в рамках курса, лекции, вебинар-вопросы. И на днях, в апреле или в начале мая, мы организуем с Андреем Владимировичем, это академический руководитель, он вот здесь тоже присутствует, встречу, где расскажем про программу, то есть что за курсы, о чем они и прочее. Я правильно понимаю, Андрей, что вы пришлете нам презентацию, я смогу ее выложить или прислать в каком-то широком доступе?
Да.
Да?
Я пришлю презентацию. Алина Белько. Это случайно не моя ли бывшая студентка Алина Белькова? Сейчас написала спасибо за лекцию. Мне кажется, такое редкое сочетание имени и фамилии бывает крайне редко. Надеюсь, это она. Если это она, то ей большой привет. Да, ей было любопытно. Это я, Алина, а это ты. Очень приятно. Встретить
Андрей
знакомых.
Кузнецов более намного распространенная фамилия, так что тут и имя.
Это правда.
Все,
это правда.
тогда, да?
Да, спасибо большое. Да, если какие-то есть вопросы, то
спасибо
пишите.
большое.
Спасибо. Всем пока.
До свидания, да.
Да, всем всего доброго.
До свидания.